Hi everybody, hope you're having an awesome day so far. Today we're going to continue talking about trends of properties on the periodic table, and we're going to be focusing on electronegativity today. So let's first define what electronegativity is. So electronegativity is the tendency for an atom to attract electrons to itself when it's chemically combined with another element. So we've talked already about ionization energy and electron affinity. And so remember, those are the energies that are transferred when an electron is lost or gained. So you can have a chemical bond happening by losing and gaining electrons. That's called an ionic bond. Or you can have a bond formed by sharing electrons. That's called a covalent bond. And we're going to talk more about the types of bonding in the next chapter. But for electronegativity, we're focusing on when the electrons are basically being shared. So we're talking about electrons being shared here. So for example, you've probably all drawn the lowest dot structure for water before. And again, we'll talk about bonding later. But in water, you know that this line here represents two electrons that are being shared between the oxygen and the hydrogen. And again, here we have two electrons that are being shared between the oxygen and this hydrogen. So even though these electrons are being shared, sometimes they're not shared very equally. Sometimes one atom attracts the electrons to itself a little bit more than another. So in water, the oxygen we say is more electronegative, meaning that it attracts the electrons in this bond towards it more than towards hydrogen. So they are sharing, but it's unequal sharing because both of these atoms have different tendencies to attract electrons to themselves when they're bonded. The oxygen, we say again, is more electronegative, meaning it has a higher tendency to attract those electrons to itself, compared to the hydrogen is less electronegative. It doesn't have as much tendency to pull those electrons towards it. So hopefully you did your homework and you graphed these values here. You'll notice that electronegativities do not have units. So electronegativity does not have a unit. It's a relative thing. So it's a relative measure of that tendency to pull the electrons towards itself. And so they do not have units. Also, you'll notice that the noble gases are missing. So element number 2 is missing, which is helium. Element number 10 is missing, which is neon. Element number 18 is missing, which is argon, and so on. And so we can't really measure the electronegativity of the noble gases because they don't really bond very much. And so they're not on the table. They don't even have a value that we can measure. Now, if you did do your graph, you should see that the group with the highest electronegativity values should be the halogens. And so those would be like the ones with the peaks up on the graph. And then the group with the least electronegativity should be the alkali metals. And we're going to talk about why that is in a minute. So these are the halogens, and these are the alkali metals. Now, below the alkali metals would have been the noble gases. It's just that we don't even have any values for the noble gases. So we say the values or the least electronegative are the alkali metals, but really the noble gases are even below that because we don't even have values for it. So if you look at the next page here, there's a little activity where you get to color the periodic table based on your electronegativity values. So, and the idea is that I chose that the lighter colors would be the lowest electronegativity, where the darker colors would be your highest electronegativity. So you can use any colors. You don't really have to follow this, but if you do follow it, the idea again is lighter means low, darker means high. So I'll give you a few minutes to get some colors, some crayons or some colored pencils, and go ahead and color your periodic table so we can see those trends. So stop the video, color it, and then when you're done, we can resume the video. All right, so I have the periodic table colored, and again, the idea was that the low electronegativity values would be lighter, the high electronegativity values would be darker. So it looks like the lowest values are in this corner of the periodic table, and the highest values are in this corner of the periodic table. Again, with the exception of the noble gases would even be lower than the alkali metals. So those are the lowest, and followed by this corner. And it looks like it's increasing electronegativity as you go this way on the periodic table. Again, with the exclusion of the noble gases. So let's answer these questions together. So the first question asks us, number 1, what trend in electronegativity do you observe as you go down a group? And so as we are going down a group, it looks like the colors are getting lighter. If you look at the majority of them, it looks like colors are getting lighter. So it looks like it's decreasing as you go down a group. So we'll say decrease. Number 2, what trend in electronegativity do you observe as you go across a period? So if you take a look across a period, it looks like it's getting darker and darker. And so it looks like it's increasing as you go across a period. So we'll say increasing. Number 3 says justify the reasons for your the trends observed, and your answer should refer to our model of the atom and the Aufbau diagrams or the electron configurations. So again, remember this all has to do with where are your electrons, if you have extra protons in the nucleus, what happens to your net attraction, your Coulombic attractions, or your Zeph, and why. So let's go ahead and answer number 4 before we go back to number 3 and write out our explanation. So let's look at number 4 real quick. It says, which group of elements is absent from the chart and why? We kind of already answered that. The noble gases, the numbers are absent there, and the reason is they don't really bond very much, and so they would even have lower electronegativity than anything else that it is not even measurable. So now let's go back to number 3 and answer our trends and come up with the reasons for our trends. So we're going to say that as you go down a group, it looks like our electronegativity is decreasing. And let's think about the reason why. So remember, we have two things at play here. In both directions, whether you're going down a group or across a period, we do have more protons in the nucleus, so our nuclear charge is increasing. But at the same time, we also have extra electrons, which are causing more repulsion and more shielding, I should say less attraction to the nucleus. So what is more important as we go down a group? Well, what's more important is our extra electrons are at higher energy levels or occupying higher energy levels. And so our net attraction between the nucleus and the electrons is decreasing. So let's write that down. So even though you have more protons in the nucleus, you do have your additional electrons or your valence electrons occupying higher energy levels. And so therefore more shielding. And so because of that, our net Coulombic attraction, or our net Zeph, the attraction between the nucleus and the valence electrons, is decreasing, and so it is harder for the atom to attract electrons to itself in a bond. Okay, let's take a look at the trend as you go across a period. So as we go across, we see that it is increasing. So remember again, both ways, whether you're going down a group or across a period, we do have more protons in the nucleus. So your nuclear charge is increasing, more attraction. At the same time, we have more electrons, and so we do get more repulsion. So what happens to the net? Well, as you go across, your additional electrons are in the same energy level, and so there's not much extra shielding, there's not much extra repulsion. So what is more important is that you have more protons pulling in those electrons. So we have valence electrons added to the same energy level, and so not much extra repulsion. At the same time, we have more protons in the nucleus, and so your net Zeph, or Coulombic attractions between the nucleus and your valence electrons increases, and because there's more attraction from the nucleus on the valence electrons, it is easier to attract electrons to itself. So easier for an atom to attract electrons to itself in a bond. So again, as you go down a group, what's more important is your extra electrons are being added to higher energy levels, and so the net attraction is less. As you go across, your extra electrons are being added to the same energy level, so what is more prevalent here is the extra protons pulling in those electrons, and so your Zeph or your Coulombic attractions increase. All right, let's go ahead and go to the next trend, which is ionic size. So as always, let's define what ionic size is. So you can think of it as ionic size or ionic radius, meaning the same thing, just like we talked about atomic size or atomic radius, usually meaning the same thing. So it is the size of the ion as opposed to the size of the atom, or the radius of the ion as opposed to the radius of the atom. So it is half the distance between the nuclei of two ions as opposed to two atoms. And remember, ions means that it's a charged particle. And so remember, we said we have anions and cations. So cations are the ones that are positive. They have lost electrons. Anions are negative. They have gained electrons. So let's go ahead and write that down, actually. So and cations are positively charged, and they lost electrons, whereas anions are negative, and they're negative because they gained electrons. So let's think about this. Let's say that we have sodium atom versus sodium ion. It turns out that a cation is always smaller than its parent atom. So the cation is smaller, the neutral atom is larger. Let's go ahead and write that down. So a cation is always smaller than its neutral parent atom. Let's try to think about why. Well, remember, all this has to do with the Coulombic attractions between the protons in the nucleus and then the electrons, or the valence electrons, I should say. And so if you think about this, if we lose some electrons, then your electron-electron repulsion, your shielding, gets lower. And so your net attraction is stronger. And so the nucleus is able to hold those valence electrons more tightly, more closely. And so the size decreases, gets smaller. So let's try to write that down. Less electrons mean less electron-electron repulsion, or less shielding. Therefore, your Zeph, or the net attraction of the nucleus to the valence electrons increases, and so electrons held tighter and size decreases. Okay, let's talk about anions next. So an example of an anion is maybe fluorine versus fluoride. Well, it turns out that anions are always larger than their parent. Neutral atoms are smaller than the anion. So let's write that down. So an anion is always larger than its parent neutral atom. So let's think about why. Well, an anion has gained electrons. So I still have the same nuclear charge, same protons pulling in those electrons, but because I have more electrons, I have more electron-electron repulsion, more shielding, and so my net attraction to the nucleus, between the nucleus and the valence electrons, is less, and so the nucleus is not able to hold those valence electrons as tightly, and so the size increases. So let's try to write that down. So if I have more electrons mean more electron-electron repulsion, which means Zeph, which is my net Coulombic attraction between the nucleus and the valence electrons decreases. Less attraction means that the electrons are held looser. And so my size increases. Okay, so let's say that I have a neutral carbon, and I have carbon with, let's say, a -2 charge, and then carbon with a +4 charge. Which one would be the largest? Which one would be the smallest? Well, remember, anions are larger than the parent. Cations are smaller than the parent. So, looks like this one would be the largest. And then this one would be the smallest. And then this one would be like in the middle. So if I'm increasing them from smallest to largest, this would be number 1, this would be number 2, this would be number 3, 3 being the largest. So I can compare between an element with different charges. For example, I can compare between, let's say, Fe, neutral Fe versus Fe 2 plus versus Fe 3 plus. And again, a cation is smaller than its parents, so those both with the charge would be smaller than the iron. Well, guess which one would be smaller? This one, because it lost even more electrons. And so the smallest would be this one, the smallest. This one would be the largest. So this would be number 3, and this one would be in the middle. Now, the reason why I can compare, these three or these three is because they're the same element, right? Like those 3 are the same element, so I have the same number of protons. I'm just changing the number of electrons. This one I can also compare because they're all the same element, again, all iron, so same number of protons, only different number of electrons. So I can only do that. I can't compare like Fe3 plus, for example, with, carbon 2 minus. I can't do that if they're different elements, unless they have something in common. So let's take a look at the next couple. So let's say that I have, Na plus, and I have O2 minus, and I have Mg2 plus, F minus, Al3 plus, neon, N3 minus, and let's say carbon 4 minus. I can actually compare between those. Can anybody tell me why I can compare between those, even though they're completely different elements? Think about it for a minute. The reason is all of these have the same number of electrons. take a look at them. So neon, neutral neon, has 10 electrons, right? Sodium, neutral sodium would have 11, but plus 1 means it lost 1, so it has 10 electrons. Neutral oxygen has 8 electrons, but it gained 2, so that's 10 electrons. Neutral magnesium has 12, but 2 plus means it lost 2, so 10 electrons. Neutral fluorine has 9 electrons, but negative 1 means it gained 1, so 10 electrons. Aluminum has 13, but plus 3 means it lost 3, so 10 electrons. And neutral nitrogen would be 7, but negative 3 means it gained 3, so 10 electrons. And finally, carbon has 6, but 4 minus means it gained 4, and so 10 electrons. So all of these have the same number of electrons. They all have 10 electrons. So I can compare between them because they all have 10 electrons. So I can compare between elements if they have the same number of protons, just different electrons, or I can compare between them if they have the same number of electrons but different protons. So let's think about this. Which one would be the smallest? Well, again, they all have the same number of electrons. Difference is in the protons. So which one do you think would be the smallest? Well, it's going to be the one that has the strongest attraction between the nucleus and the valence electrons, right? And so the one with the strongest attraction would be the one with the most protons, because you have lots of positives in the nucleus to pull those electrons in. So they have the highest Zeph. And so the largest out of all of these would be, the smallest out of all of these would be aluminum. That one would be the smallest because it has the most protons in the nucleus to pull those electrons towards it. Followed by magnesium. So aluminum has 13 protons, magnesium has 12. Followed by sodium. It has 11 electrons. Followed by neon. 10 protons. Followed by fluorine. It has 9 protons. Then oxygen with 8 protons. And then nitrogen with 7 protons. And then finally carbon with 6 protons. So again, for those, I was able to compare them even though they're different elements because they all have 10 electrons, just different number of protons. The ones with the highest number of protons are going to be the ones that are the smallest. The ones with the lowest number of protons are going to be the largest because these have the weakest attraction between the nucleus and the valence electrons. These have the strongest attraction between the nucleus and the valence electrons. All right, that concludes the lesson for today. Have a great rest of your day and hope to see you tomorrow.